Hey guys, how you doing today? I hope everyone is doing well. What does that button do? So, I hope everyone is... I bet that just glitched out. Anyway, hope you guys are doing well. I hope everything is working. So, trying to verify, trying to figure it out. So, we're arriving. Sorry, my encoder has changed how it works. And so I'm trying to make sure that it's working. Hi, Jenna. I'm glad you guys are rolling in slowly today. How is everyone's Wednesday? When I last saw the outside, it was sunny, but I haven't seen the outside in several hours because this room has no windows. So, as you guys pop in, feel free to drop a howdy or a hey in the chat so I know that you're here. And if you have any questions, hi Emma, you can go ahead and drop those in the chat if you have anything about any of the questions. On Monday, you guys took your mini exam. Those will be graded for sure by Friday. As soon as they're ready, I will unlock that and they will update everything in Canvas accordingly. So, other important news. Next Wednesday at this time, you're going to take exam 3. It is that time in the semester, Mary, where it's exams it feels like all day, every day. I feel the same. So all that's coming together. You will see all of that information here shortly. The exam feels like it is going to cover everything since exam 2. So that will be Chapter 7, Chapter 8, and Chapter 9. So basically the last 3 weeks. It will be, I don't want to say the same as it's always been, but it'll be pretty similar to the last couple. So does anyone have any questions before we start drawing the VSEPR structures for next week, or for today's lesson, sorry. Give you guys a second, see if you have any questions, then we will draw. So Christopher would like clarification or asked, this upcoming Wednesday is the next exam. Yes, that date is, hold on, let me actually look at a calendar because life is hard. So on April the 7th is our regular exam 3. So we have a regular exam next week, which means on Monday we will have the live session. If you can't make it, it lives on my channel and you can go back and watch the old ones. So Emma asked, is the final exam cumulative? It is. So the final exam covers everything all semester and the new material from Chapter 10. And I will give you more information on what percentage is the new material after the next exam. Because I want to say it's between 10 and 25%, but I will give you a much better, X number percent of the exam is that. So it is 7 through 9. 7 was really short. It was I think 3 videos on periodic trends. I think I'm checking to see if there's anything else in the chat box that I'm missing. I don't think so. It's looking good. Other things I will tell you, you are definitely going to need to draw. So as you noticed on mini exam 3, there was a lot less math. So there will be lots of drawing. There will be lots of name this compound, what is the bond angle here, etc., etc. So any other questions? Otherwise, we will talk about today's questions. I'm not seeing a lot of other questions. As always, if you have one, you can just drop it in the chat and I'll answer it here in a second. So today, most of what we're going to do is draw structures. So there are 5 questions, a lot of draw the Vesper structure, name the Vesper structure, a couple of other questions here and there. And then our last one is a very large molecule that we will all work on together. So Hope says, I struggle with the bond angles a little. I'm going to give you guys some tips and tricks and show you more of what it is that I will accept and what is an absolutely will not accept. Because I think sometimes when we think about bond angles, it feels like I'm asking you to get out like a protractor. I think that's what it's called, where you can actually measure the angle. It turns out that what I really want is something that looks roughly-ish right, and is definitely not 90-degree angles. So let's start with some examples. So we are going to draw the Vesper structures. So last week, we drew the Lewis dot structures for all of these. Oh, Jenna. Jenna says the chapters with math were easier for her. So if you are like Jenna and you're like, drawing isn't my friend, I really wish we were going back to the math. So here is the way that I think you should think about this. The trick, I don't like the word trick. One of the ways that this gets complicated for all of us is the fact that it feels like there are a lot of different patterns. In math, in a math question, it is often easier because you know what the steps are. If you prefer to have a clear outline of steps, my recommendation would be to make a flow chart of what you do first in what order. So that you can then kind of look at, okay, we have H2S. What does the Lewis dot structure look like? And then you can basically read off of that chart, because you should have made several charts, and then you can figure out what the structure is. So, as we move forward, if you have other questions, if I think of great tips, I will share them. So our first structure is for H2S. And so if you remember back, the Lewis dot structure looks like this. So these are, I think it was question either 2 or 3 from last week. So if you have questions about the Lewis dot structures, go ahead and ask, and we can talk about how you got there. But for these, you probably already have that. So we have this Lewis dot structure. So the thing is, there are only 5 base geometries: octahedral, trigonal bipyramid, tetrahedral, trigonal planar, and linear. All five of those come directly from how many things did I download the wrong one? Hold on. Jenna says that these are not the right structures. I think it's the right ones. I guess let's look at Canvas and verify that I uploaded the right things. Hold that thought. I think our consensus, Jenna, is that you Jenna, I don't know what you downloaded. So now, back to where we were. So 1, I'm glad that we're all confirmed. So Jenna, it is up in the problem solving, so you may have downloaded the Chapter 9 worksheet instead. But in this case, no need to feel bad. We've all been there. So in this case, there are 4 things connected to the sulfur. Sulfur is our central atom. It's hydrogen, hydrogen, and 2 lone pairs. The 4 things means we have a steric number of 4. So we know that we're going to have a sulfur in the middle. And our base geometry is going to look something like this. I'm going to bring you guys substantially closer so that you can actually see what we got going on. So in this case, we have our Lewis dot structure, which is probably a little low. Make that shorter. And then we have this. So earlier, Hope said she struggled with the bond angles. Now, you'll notice that my bond angles will vary anywhere from this to kind of a little zhuzhing around here. A couple of things. What is not acceptable is a 90-degree angle or 180. You need to have something that looks like this. More than that is probably unnecessary. From here, we're going to go ahead and add in our hydrogen atoms. And I'm going to put mine here and here. And then I have 2 lone pairs. And they look like this. So in this case, I could ask, what are the bond angles? Or what is the name of the shape? So the electron geometry and the molecular geometry. The electron is tetrahedral. The molecular geometry is bent. And so if it asks you for both and they are the same, you can write both or something else. So our next structure, try to move that over a little bit, is PCl3. So our Lewis dot structure is going to be based on or has a phosphorus in the center with 3 chlorines, all of which need to have their lone pairs. And we have a lone pair here. So now we can count the number of items surrounding our phosphorus, which again is 4. So we're going to put our phosphorus in the center. And you'll notice that my bond angles are similar, but probably not exactly the same as they are in the sulfur structure. Oh, new comments. Whoa. I missed all the comments, my bad. So Muri asks back to this structure because I apparently missed it. So is it okay if I put my hydrogens on the left and not at the top and right? Yes. You could have put, in this case, any of these anywhere you wanted. They're all the same. So Hope asked, so for the things connected, the angles can go anywhere. They just have to be symmetrical. We also have, does it matter where you put the lone pairs? No. So the trick, it's not a trick. When we think about these structures, we are looking at static pictures. And so it turns out that in this case, this molecule can rotate and all of them are the same. So it doesn't matter where you put them. The places where the lone pairs matter, because there are structures where it does, have to do with steric numbers of 5 and 6. So trigonal, bipyramidal, and octahedral. In that case, there are rules about where the lone pair should go in order to account for the spatial relationship. However, with the tetrahedral, there is no constriction because they should all be the same regardless of how you look at that molecule. So from here, we're going to add in our lone pair, which in this case, I'm going to put it on the top, and our chlorine atoms. all of which are going to get their lone pairs. So in my class, you are required to put your lone pairs on every atom, all of them. Lone pairs that are not on the central atom do not need to have wedges and dashes, but they do need to be here in this case. So Clark asks, what would be an example where the placement of lone pairs / ligands is determined? We will look at that. Hold, please. I need to come up with a molecule. So we are now going off script. So we will come back to as many of this list as possible, but Clark asked a good question. So what would be an example where the placement of lone pairs and ligands is determined or has control over that? So let's look at SF4. So in this case, the valence electrons are going to be 6 plus 4 times 7, which is 28. This is 34. So our Lewis dot structure looks something like this. And we've used up 32 of our 34 electrons. So then we will have our last two on the sulfur. And so Clark's follow-up question is, will this be on the exam? So it turns out that in this case, so when we want to draw our Vesper structure, there are 5 things connected to the sulfur. 1, 2, 3, 4, 5. We have 4 fluorines and a lone pair. So in this case, the sulfur goes here in the center, and our 5 things makes it a base trigonal bipyramid. If you look at the graphics that I've provided for you, both in the video and in the packets online, you can see that there, when we think about the trigonal bipyramidal, there are, based on the electron geometry, they're all trigonal bipyramidal, but the molecular geometries have different numbers of lone pairs. So in this case, this only has 1, and it wants to be as far away from everyone else. So it goes here. And the fluorines end up here. With all of their lone pair friends, which, yes, takes 300 days for you to draw. So now, in this case, for this molecule, the electron domain or the electron geometry is trigonal bipyramid, and the molecular geometry is seesaw. Or it has another name, and I don't remember what it is. Seesaw, or I think just seesaw works. Sawhorse is the other one. So in this case, it is wrong if your lone pair is in either of the axial positions. You could put it, because this rotates around the equatorial, so the center, you could put the lone pair in either of these positions, and that is the same shape geometrically, but it cannot go in either of the axial positions. So for anything with a steric number of 5 or 6, so base trigonal bipyramidal and base octahedral, you have to think about where the lone pairs on the central atom go. For tetrahedral or trigonal planar, it doesn't matter. Does that? Here is one example. So it looks like we have a series of similar compounds. So we are going to look at COH2 next. So our Lewis dot structure should look something like this. Instead, oh, wait a minute. Let me move this back over so you can see. So we have this formaldehyde group here, COH2. And so we need to ask, what does the Vesper structure look like? So a Lewis dot structure has three things. And so now this is trigonal planar. And your bond angles are 120 degrees. So Muri asks, the best thing is to put the lone pairs on the sides. No, kind of. So the best thing to do is to think about, so Muri asks, is the best thing to do to put the lone pairs on the sides usually? The problem with that assumption is that it doesn't always work. And the moments when it stops working are typically when you start to have more than one lone pair. So lone pairs want to be as far apart as humanly possible. In things with steric numbers of 5 and 6, there are different arrangements by which that can occur. So it means that for if somehow you had this similar arrangement, but now you had two different lone pairs. So if you had two lone pairs, then they would want to be across from one another so that they could be farther apart. Right? No, in that case, they would go here and here, so they would be further apart. The graphics on Canvas are the ones that I'm going to ask you about. They should follow those trends. There are a few tricks in some of those, but all of that, there is a table there's one that you filled out, and in that document at the back, there's one that's previously filled out for you. I would stick to that. Other questions about any of the examples that we've talked about thus far? Oh, sure. So for PCl3, the molecular geometry was still tetrahedral. And nope, that was the electron. The molecular geometry is trigonal pyramidal. Good question. Other questions? Let's do, so it turns out that the ammonia and the two different carbon-based CH2Br2 or CH3Cl are going to look very similar. So I will do the CH3Cl, and then we can move to the next question. So we have CH3Cl. Our Lewis dot structure looks like this. So in this case, our there are 4 things connected to our carbon, which makes it base tetrahedral. So we're going to pop our carbon here in the center. We're going to put our 3 hydrogens and our 1 chlorine. All of these are the exact same. Both the molecular geometry and the electron geometry are both tetrahedral. So, based on this information, what is the hybridization of this carbon? So, when you come up with an answer, you can go ahead and drop that right in the chat box. Yes. While you are thinking about what the hybridization in this molecule is for the carbon, what questions do you have about the first several structures that we've drawn for Vesper structures? We've got an sp3. Very good. So Muri and D to the first D both say that it's sp3. Both of them are 100% correct. We've got Ashana and Daquan both giving us sp3 as well. That is 100% correct. So hybridization will likely be approached on the exam as, what is the hybridization of this atom? Either in a molecule that you draw or in a molecule that I provide for you. So this molecule here is sp3 hybridized. And so as we kind of go forward, I don't think it asks specifically about hybridization on any of the questions, but we can always kind of ask ourselves about that. So our next question, is about sigma and pi bonds. What is the major difference between a sigma and a pi bond, and how many electrons are in each bond? So a sigma bond and a pi bond, we're going to answer the second part of this question first. So each bond has 2 electrons. And that is true for either a sigma or a pi bond. So the difference between these two has to do with their orientation. So when we think about a molecule, a sigma bond is along the nuclear axis. And a pi bond is above or below the internuclear and a pi bond results from pure p orbitals. So a sigma bond typically is created out of hybridized orbitals. So a sigma and a pi bond, the difference is if you have 2 compounds joined together, this is our sigma bond. It is between the 2 nuclei, which are at the ends here. A pi bond would be created above and below the internuclear axis. So the sigma bond is created of 2 electrons. A pi bond is created of 2 electrons. The way that you'll see this on the exam would be to be asked, in this molecule, how many sigma bonds are there? So looking in this molecule right here, how many sigma bonds are there? So in this case, our sigma bonds are any single bond, 1, 2. But in this bond, the first one is a sigma bond, the second one is a pi bond. So in this molecule, there are 3 sigma bonds and 1 pi bond. So in the chat, we were asked, lone pairs count for hybridization. Yes, provided they are around the central atom, they always count for hybridization. Good question. So what questions do we have in general about sigma and pi bonds? If you have no questions about sigma and pi bonds, you can go ahead and drop none right in that chat box so that I can figure out if we're all following along. If you have questions, you can drop it. Ooh. So Muri asks, what happens if we have 2 pi bonds? So in the case where we would see that, that would be nitrogen gas has in this case, both the Lewis dot structure and the Vesper structure would be the same. So in here, we would have 1 sigma and 2 pi, so the only time you will see 2 pi bonds is if you have a triple bond between 2 atoms. Otherwise, you can have more than 1 pi bond in a molecule, a much larger molecule though. Oh, so like CO2, the structure of CO2 is so in this case, this molecule would have both 2 sigma and 2 pi, where in between each oxygen and carbon has 1 sigma and 1 pi bond. In the video, it talks about, I think it talks about the spatial relationship between where they are. But you can have more than 1 pi bond in a molecule, and you can have more than 1 sigma bond, but only 1 sigma between 2. So our next question brings back, I don't want to say everyone's favorite topic, but polarity. So the first thing we want to think about is which of these molecules is polar. Now, if we were to think about these bonds, all 4 of these bonds, BF, CF, PF, and XEF, are all going to be polar bonds. They're all involved with fluorine. So the question in this case now comes down to structural arrangement. Polarity, if we think about this in terms of more than 1 element pulling away, so between boron and fluorine, that's a polar bond. Same with carbon and fluorine. All of these are polar bonds, but we're asking which of these molecules is polar. So in order to answer that, we need to draw Vesper structures and look at the arrangement of polar bonds. So I will start by drawing all 4 of our Vesper structures, then come back and ask which of them has polar bonds in an arrangement that makes a polar molecule, and what is the dipole moment of that molecule. start with BF3. Yep. So BF3, we have 4 valence electrons. We have 3 plus 3 times 7. That gives us 24. Put our boron here in the center. We're going to connect it to all 3 fluorines. We're going to add all of our lone pairs. So we've now used all, I think this will work better. Sorry. Get a little bit closer so you can see what we're drawing here. So we have BF3. Now, one thing you might be like is, ooh, boron doesn't have octet. It turns out that boron, like anything else in that same column, can have less than octet. So this is a valid structure, which means it has a steric number of 3, which is trigonal planar. So we're going to put our boron here in the center. We have 120-degree bond angles. And so we can either ask ourselves now, is this polar or not? And we will, because I think we're going to have some space issues, because I'm trying to get you guys close enough to see. So in this case, while this bond itself is superpolar, this is a non-polar molecule. And it's non-polar because while all of these are polar bonds, they all pull at a specific angle at 120 degrees. So no one bond creates a polar molecule. Now, we're not really going to add and subtract vectors. I like to think of this as a tug of war. Boron and fluorine are in a tug of war, but it turns out that boron is being tugged in 3 directions, but all by the same element. So no one of them can hoard the electrons more than anyone else. So polarity arises when either one bond or all of the bonds push the electron density in a different way. So let's look at CF4, which is just the next molecule on the list. So we have CF4. The valence electrons are 4 plus 7 times 4, which is 32. We're going to draw our Lewis dot structure first. Then we're going to add all of our lone pairs. And so we've used all of our electrons. So because there are 4 things connected to the carbon, we know it's base tetrahedral. We're going to add our fluorines. Don't forget your lone pairs. So we have this arrangement here. Now, in this tetrahedral molecule, all of these bond angles, instead of being 120, are actually 109.5. So again, we have the same situation of a series of polar bonds, but because of the arrangement of this, these are non-polar as well. So a non-polar molecule and a non-polar molecule mean that 2 of our 4 are non-polar. In this question, it just asks which one is polar. So far, we have 2 non-polar. So I'm going to move the screen. I'm just going to move it over. So next, we're going to draw PF3. Our Lewis dot structure is going to look like this. So from here we can draw our Vesper structure, which is also base tetrahedral. Whoa. In this case, I put the lone pair for the phosphorus on the top. So this one looks a little different. Thus far, all of our molecules have all had the ability to say, like, they're all the same. So now we have 3 bonds. And in this case, the electrons go in this direction. But because there isn't PF4, this is considered a polar molecule. And so the overall dipole moment for this molecule could be calculated. It's a little complicated just due to the arrangement here, but overall, this is a polar molecule because of the lone pair. Unless the bonds are not polar, any compound where there's only one lone pair on the central atom is likely polar. If it's composed of polar bonds, more than likely it's polar. So let's look at our last question, because while it doesn't say which one of these, it says which of these. So let's look at that last one and see if it's polar too. Oops, sorry, cords. So over here we have our last one, which is XeF2. So our valence electrons are 8 plus 2 times 7, 14. 22, I think. We'll figure it out. So we have Xe connected to 2 Fs. So this is going to use 16 of our valence electrons. So we now have 3 sets of lone pairs around our central atom. Now, xenon is a noble gas. We typically say that noble gases don't make bonds and they don't interact. It turns out that some of them can. We also now have 2, 4, 6, 8, 10 electrons surrounding our central atom. But because it is below phosphorus and over, we know that those can have more than octet, up to 12, no more than 12. So you may have 6, 8, 10, or 12. Those are really the only options. So from here, we need to ask ourselves, what is our base geometry? There are 5 things connected to the central atom. So that is base trigonal planar. Nope. It is base trigonal bipyramid. So now we need to ask ourselves, where should we put these 2 fluorines? They want to be as far apart from one another as possible. So we're going to put them here on the axial positions with all of their lone pairs. And then the 3 remaining lone pairs are here on our central atom. And because of this polar bond are 180 degrees from one another, and so this is also non-polar. So the only polar molecule we had was PF3. What questions do we have about molecular polarity, or any of these structures, or how to create structures, or anything else? If you don't have any questions, you can go ahead and write none in the chat box, or send an emoji my way, so that I know you are ready to move on to drawing more Vesper structures. Max would like to know how he got here, and I'm guessing you clicked a link. Welcome to Gen Chem 1. D to the first C has no questions, and that's excellent. Hope says, I think she's doing okay. Not a fan of the drawing, but that's okay. We're going to get you there. Otherwise, I will go ahead and put up our next question. I'm not seeing any other questions. I'm going to go ahead and start erasing the board so that we can start looking at these next structures that we're going to draw. Ooh. Mary says she's ready for more. Good. So in this case, we have 5 different structures that we're going to draw, and we want to name the electron and the molecular geometry. So I've been using the word base geometry, which is just another way to think about the electron geometry. The molecular geometry is always a subset of the electron. So our first compound is PCl5. And so in this case, the valence electrons are 5 plus 5 times 7, and that's going to give us 40. So we're going to put our phosphorus in the center. We're going to connect all 5 of our chlorines. We're going to use all of our lone pairs. Uh-oh, forgot a pair. So we've now used all of our lone pairs. In this case, once we have this Lewis dot structure, we can now go on to draw our phosphorus structure. There are 5 things connected to our phosphorus, which means it is a base of trigonal bipyramid. We know that base looks like this. We're going to add our chlorines and all of their lone pairs. So we have this. Now it asks us what the molecular geometry and the electron geometry. We're going to say both trigonal bipyramid. So on the exam, I'm going to ask you this. For maybe a molecule like this where they're both the same, if you just write trigonal bipyramid one time, you are going to lose points for one of them because you didn't answer both. So your options are to write EG/MG, trigonal bipyramid, or you could say both trigonal bipyramid. You basically need a way how to say, I know that they're both the same. So in this case, for this molecule, this is what it asks you. What questions do you have about this molecule? Or are we ready to think about drawing ACl3? I'm going to let you drop your questions in the chat box. There seems to be a weird lag today. And I'm going to start on the next one. So if you've got a question, you can drop it in the chat. If you don't, you can drop none in the chat or nothing. So our next question, our next molecule, is aluminum trichloride. So we have, this is our Lewis dot structure, which has 90-degree angles. And aluminum can have less than octet. just like phosphorus can have more than octet. So now that we have three things connected to our central atom, we know that it is going to be base trigonal planar. Don't forget your lone pairs and some pretty good looking bond angles. And so the molecular geometry and the electron geometry are both trigonal planar. Question. Oh. Hope asks, why are these names so crazy? I have no idea. I didn't name them. I would have named them, I don't know, something a little less interesting, you know. But I can't think of any other way to think about it. I will tell you that there are different names for some of these. So some people may have learned other names for trigonal bipyramid. So sometimes it's trigonal bipyramidal or just bipyramid. I will accept both. Neither one is more right or wrong than the other. And as long as your spelling is mostly close, I will take it. If you write tetrahedral and you meant something else, that's not a spelling mistake. But if you don't know how to spell tetrahedral and it kind of looks like it, I will give you credit for that because spelling is not my strong suit. Questions? So next, yes, I have plenty of space to draw the next one, and then we will move over there. So we're going to look at BrO2 minus. And so last week we drew a Lewis dot structure that looks like this. Oh, before we move on, Yuri asks, what's the hybridization of PCl5? Is it sp4? So it turns out that hybridization for elements above steric numbers of 5 is still pretty much up for debate. You may have heard that this would be sp3d hybridization. In my class, the evidence for dehybridization is a little murky at best, in my personal opinion. So we will only look at dehybridization for anything with steric numbers of 4 or lower. So that is trigonal planar, that's tetrahedral or linear molecules. Those are the only times we're going to see it. And so we'll have SP, SP2, or SP3 hybridization. Anything beyond that doesn't hybridize. So this aluminum trichloride has an SP2 hybridized center, and this phosphorus does not have a hybridization at all. Great question. So in this structure, using the information that we know that there's 1, 2, 3, 4 things connected to our central atom. And so they look something like this. We have 1 oxygen, we have 2 oxygens. So I'm going to put my 1 here, 1 here. And we have our 2 lone pairs here. So in this case, we have a double bond. If you try to draw a double bond in a wedge, it gets really complicated. You can do it. It would just be 2 wedges or 2 sets of dashed lines next to each other. So in this case, we have this molecule to where the molecular geometry is tetrahedral. And the electron geometry is bent. Questions about any of these molecules? So our next molecule is BrO2+. And so last week we drew our structure. It looks a lot like this. Lots of questions happening. So BrO2 minus, so Miri asks, will have 4 sigma and 1 pi bond? No. So the lone pairs don't make a bond. A sigma bond or pi bond requires 2 elements to be on either end of that. So in this case, it would have 2 sigma and 1 pi. The lone pairs, while we count them in terms of the steric number, it doesn't take into account the arrangement. They don't count as bonds. Good question, though. Let me move this over a little bit. So from here, we look at this structure, and there are just 3 things connected to our central atom. So in this case, our bromine, we're going to have our lone pair here at the top with its positive charge. We have our 2 oxygens out here. Here. And so now we have this molecule where the electron geometry is trigonal, planar, and the molecular geometry is bent. And these are backwards. Questions as I stand in front of stuff. So for BrO2+, we see a substantially different structural arrangement than for BrO2-, which makes sense. We've added or taken away a whole pair of electrons. So our last compound is GeHCl3. And so our, too close. Our Lewis dot structure looks like this with all of its lone pairs. So from here, we now have this structure. There are 4 things connected to our central atom, which means it is base tetrahedral. And so in this case, both the electron geometry and molecular geometry are tetrahedral. And the hybridization of this is sp3. This one was sp2. So, based on all of these structures, what questions do you guys have about drawing VSEPR structures of small molecules? So, in a second, we are going to draw our last molecule, which is way different. It is something a little bit different. If you've looked at the structures, it's perhaps a little terrifying, but that's okay. If you have no questions, you can drop none right in that chat box, or you can give me an emoji or anything else that says that you are ready to draw glutamic acid, which is what we're going to draw. Ooh, we have some questions. So when drawing, Clark asks, when drawing VSEPR structures, do you want us to draw the Lewis as well? Yes. On the exam, it will say, For this molecule, draw the Lewis dot structure and the Vesper structure, including the names or anything else. So if it asks for both, you have to put both. If it doesn't, you don't need to include the Lewis dot structure. Ashana asks, would GeCl3 be a polar molecule? I think so. You may have to look at the actual electronegativities of germanium, of Ge, but if it was, if perhaps instead of Ge it was carbon, that is polar because of the different polarities for carbon, for chlorine versus hydrogen. But I do think it's polar in that case. Hope asks, is something like the last one going to be on the exam? Maybe not exactly like that, but something similar where it is a much bigger molecule where we can start to think about that. So I am going to move this up here and add that. Now I'm going to erase the board. Then we're going to draw this molecule. So in this case, this is a much, much larger biological molecule. So I see Mary's given a stressed face. Now, a couple of things. I want to talk about why this, while it can be intimidating, isn't quite as intimidating as it might feel. Number one, I'm not going to give you the formula for this and then be like, please draw this molecule. If I give you a Lewis dot structure that looks like this or any other arrangement of atoms, you have all of the skills today in order to answer that question. So, my dad likes to always say, like, you can do anything one bite at a time. Well, it's usually you can eat anything, but like that seems a little excessive today. So in this case with this molecule, I'm trying to make sure I'm not behind this screen, what we can do is start to look at each individual atom. So there is, you can see a linear line at the top and then a vertical line going down. Those are your central atoms. And so we want to make sure as many of those as possible are in the plane of the board. The other thing we kind of want to start to think about is where do they go and what do they look like? So I am aware that this feels super complicated. That is not necessarily surprising. So the other thing to think about with this is to, on the exam, I would straight up hold my piece of paper in front of it and only look at one central atom at a time. It works a lot better when I can cover things up, but digital life. So instead of looking at the whole thing and panicking, look at only that nitrogen that's right next to my finger, which is over here. So instead of looking at all of it, let's just look at that part and see what we can do. So I'm going to start down here. And we have our arrangement, which is a little bit different. All right, yeah. And then I'm going to put my hydrogens, and we're going to connect to the carbon. So there it is. So we now have a carbon. So we have a nitrogen followed by a carbon. This carbon has a double bond oxygen. And then we have an oxygen. that is also steric number of 3. So I know that I'm drawing this quite quickly, and you're feeling a little like, okay, I don't know what just happened here. So I'm going to redraw the Lewis dot structure. So this, I flipped this molecule around. Let's see if I can actually do that on here. Nope, turns out I can just make it bigger and smaller. So when we look at this, and the one on the exam, well, if it's this kind of molecule, will be in a different arrangement. But the thing is, let's just look at each one of these. So in this case, we know that this nitrogen has 1, 2, 3, 4 things connected to it, which means it's base tetrahedral, which is what we drew here. So what about this one? 1, 2, 3, 4 things. Oh, also tetrahedral. Trigonal planar, it has 3 things connected to it. Tetrahedral, it has 4. Don't be afraid to look at this molecule and only pick certain parts. Draw what you can. Now, you have to have wedges and dashes. This one goes on to ask a variety of other components, which we will get to. And we may not finish this before 5:45, so if you have to bounce, feel free. I will include all of the answers at the end of the video, like the usual way. I'll just stay till we finish. So from here, we've started this. Now, I want to address the way that some people tend to draw their structures. It tells you need wedges and dashes, and so a lot of times what I see students draw is this. So this feels like it has the right things. You've got some wedges and dashes, and you have the right number around any of these. However, all of these are 90-degree bond angles, and none of these are. So it's important to note that I'm asking you to draw this type of structure, not this. This will get you very few points, because all you did was erase some of the lines and make them wedges and dashes. So let's continue upon our molecule. So we have drawn over here, we've drawn this top part, and now we're going to go down this side chain. So in this case from here, we have a hydrogen, followed by a carbon, which has 2 a hydrogen, another carbon, two hydrogens. Here we have another carbon, some mediocre 120-degree bond angles. And out here we have an oxygen, now, a couple of things. I'm going to move this over here to where it's not on my face. This is by no means perfect. This doesn't really look 120 degrees. It looks close. It's somewhere between. So it doesn't have to be perfect. As you advance in your chemistry courses, this will become much, much, much easier. Today, what we want to think about is how to look at Lewis dot structures of bigger molecules and draw them. In this case, what we're going to do is we're going to attack each individual steric center, basically anything connected to something else, and ask, what does that look like? What is the hybridization for this? So, what questions do we have about this? All right, so Hope says she feels lost. So, when we think about this structure, so I'm going to leave this here. I'm going to draw something else over here. If I were to give you this structure, so let's leave this molecule alone. I'm going to bring us over here. Whoops. And so let's look at this molecule. Because maybe this one, well, I like it, maybe it's too big and too bulky. So instead of glutamic acid, so this doesn't exist, but this does. So in this case, it's a little bit easier maybe for us to think about it. So we have relatively clearly a backbone in this molecule. In this case, we have the ones squared in blue that my head is in front of. So these are all of the molecules that are probably going to be in a row. So instead of looking at this molecule and saying, I don't know what to do, which is frankly always the first step, but let's start with any one of these. So I'm going to start on the left side because it's just the left side. So from here, hydrogen isn't really a steric center. It doesn't have anything connected to it. But this oxygen is. So right now, we could say this is the molecular geometry, no, the electron geometry is tetrahedral, and the molecular geometry is bent. Because we know that it has 4 things connected to it, 2 atoms and 2 lone pairs. That's what this is. So from here, we're going to put our hydrogen. We're going to start with our oxygen, which is going to look something like this, which looks like all of the other ones we've seen, hydrogen at the top, carbon down here. So now we're going to look at this carbon. This is electron and molecular geometry tetrahedral. So we have this. And I'm going to draw it like that. So one of the things that gets hard is trying to figure out how do we arrange these in space. Anything in this box, we want to draw, if we can, in the plane of the board. So we have our 2 hydrogens back here. And we have a trigonal planar that looks like this. And our last one is another tetrahedral. And so we're just going to put our 2 hydrogens here and put our last chlorine here. So we had a question in the chat box where Ashana asks, does it matter which elements we put where on the VSEPR as long as we're connecting them to the right atoms? No. It does not matter where you put what. So in this atom right here, you could have rearranged any of these in any way you'd like. From the oxygen, however, the oxygen has to be connected to the carbon. So you are correct that there is variety in arrangement based on this structure. So in our new molecule, which is not the same as this molecule, let's think about what these structures are. So, oh, right. I like that you can kind of picture it. So from here, for this atom, we know that it's tetrahedral and bent. We also know that it is sp 3, hybridized. Because anything that is the electron geometry of tetrahedral has to be sp3 hybridized, period. That's just how this works. So for our next one, it has 1, 2, 3, 4. So both the electron and the molecular geometry are tetrahedral. Yes. We have Eg, Mg, tetrahedral. And this is sp3. So for this one, it has a steric number of 3. And so this is going to be trigonal planar for both the molecular geometry and the electron geometry, and it's going to be sp2. So for this one, it's going back to, it's actually the same as this carbon over here. The electron and the molecular geometry are tetrahedral, and it's sp3. So in this case, or in this case, you just need to look at the Lewis dot structure. And I think, in hindsight, this molecule is probably a little bit overwhelming for today. But I think with the skills that you have and the more often you practice, the easier it will be. So what questions do you have about, is there anything that I forgot to give you on this one? I don't think so. So what questions do you guys have about Vesper structures, about hybridization, or anything else from this week's videos? Oh, hope, not a problem. I am always glad to help, and I think this molecule makes a little bit more sense. So I like this example as well. I'll step out of the way so you can see it. Any other questions today? Any other thoughts? Otherwise, you guys can say goodbye in the chat, and I will see you all next Monday for the Exam 3 review session. If you have questions, you can email me, and I can add them into the list of topics we'll talk about. Otherwise, y'all have a fantastic rest of your week, and enjoy the rest of your Wednesday. Oops. I'll hang out for a second in case anyone has a question, but otherwise, y'all have a great rest of the day. So Miri asks, can we count the sigma and pi bonds? Sure thing. We'll start with the glutamic acid. So there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 sigma bonds. And there are 2 pi bonds in this molecule. In this molecule, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 sigma. And just 1 pi bond. Good question. Thanks, Jeffrey, thanks for coming. Oh, yeah, Miri, happy to answer your question. Just kind of forgot about that part. Any other questions today? If not, y'all have a great rest of the day. I'll hang out here for another couple of seconds, and then feel free to email me if you have questions. Otherwise, I will see you next week.